Now, Pedro is giving us a nice talk on planning tasks and execution. Maybe it's queuing up. We see now we are able to perceive objects and so on, and now we can do something with it. So, yeah, thank you for being here. The stage is yours, and
yeah, thanks for inviting me. It's really great to be here and to talk to all these people. So I hope you enjoyed the talk and that we have some nice conversation afterwards, which is the important part, I guess. I'm going to talk about planning task execution from user requests. I guess if it's not clear, just by the title, it will be clear when I explain it next. Just wanted to say that the first author there is a PhD student that just finished, is now a postdoc in our lab, and since he coordinated some of the efforts of the team that I'm going to show results from, I thought it would be great to put his name there. Let me just quickly tell you before I really start where I come from, and also to kind of advertise a little bit our institute so that you people who don't know it can know it better. Well, that's Lisbon. Maybe it's not clear over there in Portugal, and there's IST somewhere over there in the middle of Lisbon, and then you can see the campus. And then this is not so clear, but there are two towers over there, and one of them is where the Institute for Systems and Robotics is. So it's IST is the largest faculty of engineering in Portugal from the University of Lisbon, and there are several research institutes. The ISR is one of them. Currently, I am the president there, and I am also the coordinator for several years of the Intelligent Robots and Systems Group. And that's where the advertise comes. I mean, you can see several of the things we are doing there, and it's just a small sample. But we really go land, sea, and air, even space. There's, for instance, an experience made with the Sphere system in the International Space Station some months ago, and several times, actually. We have a lot of stuff on domestic robots, which is what I'm going to talk about today. We have an iCub in the group of José Santos Victor that Júlio Sandini mentioned the other day. They also have some nice wheeled robot inspired by that. There's a lot of great work on underwater robotics and marine robotics in general by the group of António Pascoal. And yeah, we also did some outdoor stuff with the mobile manipulators and quadrotors. And there's also groups who don't actually do robotics. They do signal processing, optimization, network systems, machine learning, and also a group which is not even depicted here on biomedical engineering. So it's quite diversified, and we really cover a lot of different things. Most of the work is in robotics, but not really limited to that. And well, it's not written there, but we are always hiring because there are always opportunities for people from projects and even from the funding of the institute. We have EU projects, national projects. And so if at some point you are interested, let me know, and there will be calls for sure in my group or other groups of interest for some of you. Okay, so here's the outline of my talk, and let me just quickly go through it now so that I give you at least the idea of what I want to go through. I'm going to talk about, exactly as Jorn was saying, I'm going to look more into the integrated system, which of course requires that some great work like Rudolf just presented is working fine for detecting objects, grasping, and so on. But I'm really going to look at the say, higher level picture here, though we are doing some stuff also on object grasping and so on. I'll try to highlight what are the things which we take off the shelf and the ones that we do ourselves. And doing so, I will be focusing on service domestic robots. That's why I start with some requisites which kind of pave the way for what I'm going to talk next. Then I do a small detour, which is important for me for a lot of reasons and for the presentation. I'll try to convince those of you who are not convinced yet about the value of robot competitions, which is something that has been my passion in research all the time. And because I'm going then to show some of the work we did is really inspired by what we had to develop for the competitions. And we take it as a research project for years. We have had several PhD students and master students doing case studies on that. So I really wanted also to take some time to talk about that, show why it's interesting, and then illustrate some of the results in the end with some of that. Yeah, and then I'll go more into what is the core of the talk, the comments to execution pipeline, the representation of plans, and the knowledge representation we use, which is, I mean, we went through several, but we'll focus on a particular one, which also has been subject of work of several students over the years, and I want to tell you some of the features it has. And then I'll show you the results, depending on time, more or less, essentially based on videos of the full system working in several settings in an apartment, and a final slide with some open challenges. Okay, that's it. Let's go for it, because we don't have much time, and I should really focus on the core. Well, as for requisites, I mean, I think we may agree or disagree in some of these, but most of you probably have heard about at least some of them. What I really want is not so much to discuss what are the requisites, but more to, as I said, to pave the way for what I'm going to talk about next. So I argue that if the service robot interacts with a human and the human gives the commands and then the robot has to find a way of executing them, of course it has to have the ability to receive and interpret those commands, and it could be by voice, by gesture. We are going to be fundamentally looking at voice commands, but that's not the important part here. It should be able to map the commands into executable tasks. So meaning not only that it has to interpret and plan, but then really has to execute the task, so it has to do the full thing. And also very important, but sometimes kind of forgotten, is the way you interact. You really have to dialogue, because sometimes the robot will not interpret correctly or will not understand fully what you are asking it to do, and it will have to find a suitable way of dialoguing with the humans to fully understand, for instance, to complete understanding what is the action or the arguments of the actions that you want it to apply. Of course, it has to keep updating. It has to keep having. I'm a control guy in my original background who started doing a lot of stuff with AI people. So I always care about talking about feedback. I mean, you really need to keep an eye on what the environment or what is happening in the environment, and keep changing your execution to adapt to that. And then I called it, I don't know if I should call bonus or something else, but it would be good, and this is kind of a more difficult goal, it's one of the goals somehow of the EU-ROBIN project, to adapt the common interpretation and execution to the robot hardware and software capabilities. I mean, it would be nice if you have this full system that runs, but then if your robot has a part that fails, or if your robot does not have a manipulator, so you know immediately what you can do or you cannot do without the intervention of humans, or even if you can do it some other way, and that. Okay, so about robot competitions. For ages, I mean, I started in robot competitions just occasionally and not even knowing about what it was around 95. And then the big thing was, for me, was when I started getting into RoboCup in 1998. Michael was there, actually. I also met him there for the first time. And the thing was that, of course, it was a lot of fun. And maybe we were not even understanding what we were getting into. And initially, a lot of people were looking at it just as yet another educational activity. Right? It's nice. The students can learn a lot of stuff working together and facing complex systems. But indeed, over the years, many of us, and for sure myself, understood that if you look at it the right way, it can be a way of pushing you to engage into serious research with complex problems, and even having ways of comparing your results with others, kind of a new paradigm, instead of, I would say, in parallel with, because I value also the other way around, of just going to conferences, presenting papers about your favorite result of a specific system, showing it at work with a lot of other people competing with you and cooperating at the same time with you, because that's what happens, and being able to show the pros and cons, the difficulties, sometimes things which are great but which are not versatile enough to adapt well to a particular environment. And so this became really something that I value a lot over the years. Usually there are, I mean, you can think of competitions versus challenges. I have two videos that illustrate that somehow, adversarial versus non-adversarial. And of course, a lot of impact can come from it, and I'll show some of it. One of them, which is very important, is we must ensure that the scientific value is there. I mean, if you are just solving that problem with a specific focus and not looking at a more general solution, it can be nice from an engineering standpoint, but not so interesting scientifically. There's a lot of technology transfer coming out of this, and I'll show some examples. And of course, education, engineers, computer scientists, particularly for this type of robot competitions we are talking about, remains very important. Some examples of success, and maybe this is already an old slide, so maybe if I had investigated a bit better, I would get even more recent ones for sure. But there are very well-known ones, like from the Darpergan Challenge, the Google car. I don't know if all of you know, but the Kiva systems from Amazon, Kiva was funded by Raf D'Andrea, who was and he always mentions that whenever he's interviewed, who was a successful competitor in the RoboSoccer small size league, and he said he got a lot of inspiration of what they did there for building these robots. And another type of technology transfer slightly different was the Aldebaran Now. I mean, the company really had started the robot already, but they really became pervasive and famous and used by a lot of people, and more robust actually, because of the way they were used in RoboCup in the new standard platform league. It was back to 2007, I think, when there was a call and the competition between several companies, and they proposed the Now. Okay, so sure, I don't want sound, so. Two examples of robot competitions. On the left, RoboCup Soccer Adversarial Challenge type of, and what I want you to, well, besides I'm just showing not showing the full video, but this video shows a lot of people attending a game which is not, oops, I'm sorry, my mistake. I just wanted to go here a little bit ahead. When you see the game going on, if you look carefully, you might think, well, it's nice, but it's nothing more than some nice engineering. There's a lot of things here, robotics-wise, which are amazing. I mean, the robots know very well their localization. The robots can act as formations. They have their roles. The goalkeepers and all the robots, but in particular the goalkeepers, have to track the ball in 3D, which is hard. This is already from 2013. Things have even evolved better than what you see there. There's also a lot of strategy already involved. I mean, there was one that I could not call your attention for when in the previous part of the video, that the robot actually was scoring a throw-in, and one of his teammates was getting to position to avoid the other guys intersecting the ball. And they communicate, they do this kind of cooperative strategies. Another example, this is actually from us, and that where we participated in the MBZIR competition in Abu Dhabi 3 years ago, is of the type non-adversarial, and this is more challenge, like what we used to say. I mean, in RoboCup, the thing is you have, and this is actually non-challenge, it's more competition. In RoboCup, you have a challenge that goes over the years. You want to have a team of robots that defeats the human team world champion in 2050. So you continue improving the rules and pushing the scientific problems over the years. Here, what we had was a few challenges which had to be solved that year. And one of them was to put bricks on the top of a wall. We had, in this case, a mobile manipulator that everything is autonomous, is watching the bricks, is deciding what is the sequence which is sent to it just before the task starts. And then it had to do it, this was indoors during the training, but then it had to do it outdoors in a realistic scenario, but outdoors. And indeed, including, you don't see here, well, it's there, including quadcopters and ground robots that would cooperate to build this wall, each of them with different participation. So I don't want to, this is not so much to illustrate what we did or we did not, just to illustrate different types of competitions, the challenges they bring, and why they can be interesting. Now, we started into this with a project in 1997 called Society of Robots. And just a few months later, Manuela Veloso was already very active in RoboCup, came, I mean, she's Portuguese, she usually would go there, gave a talk and told us about RoboCup and said that we really had to go. No way you don't go to RoboCup since you have a project on cooperative robots. So it was the first time we heard about RoboCup, and we also put in the name of the project the soccer robots, which also fits very nicely with soccer. And so we started doing that, and we were in RoboCup Soccer until 2000, from 98 to 2012, I think. And then we moved to RoboCup at home in 2016. And here we really have several research topics that we tackle. Some more, say, deeply than others. But of course, some of the things we did ourselves, mapping, localization, and navigation, including multimodal navigation in the sense of following people, not just going from waypoint to waypoint, but including following people, yeah, that's it. That's essentially the two things. And of course, avoiding obstacles. Perception, object detection, of course, people detection, grasping pick and place as well, and a lot of, and this is what I will focus most today, of decision making at the level of planning, but also of plan representation, plan analysis, using methods for that, and of course plan execution. And more we are getting into human-robot interaction, and that's why I highlighted some of the requisites in the beginning as important in this direction. Okay, so let me just take a quick look at the architectures of service robots. I will tell you a little bit of things which are more historic, to then go, I mean, to kind of justify why it is important, if that's not obvious already for you, to have architectures in order to put together our different subsystems and not just care about each of them separately, not thinking about how they connect with the other systems. I mean, when I was a PhD student, there were a lot of discussions that I think were a never-ending story that still lasts today about the best architectures. And we were not just talking about hardware or software architectures. Like ROS, the ROS middleware is kind of a software architecture in a sense. We were talking more about functional architectures. And in fact, when I say we, I shouldn't. It was more people like Rodney Brooks, like James Albus, like George Saridis was actually my advisor. And they had a lot of discussions about this. And there were two major lines. One were the hierarchical or horizontal functional architectures, where basically all the modules have access to data and they just compute what they have to do, and then they decide how to actuate, and of course they have to coordinate that, and that's also where the name subsumption comes from. And the other one, which was more classic, was the hierarchical architecture, where basically, and in this case I kind of already instantiated it for more modern stuff, but basically you have down here the control part and estimation and guidance, navigation and control of the robot, and up there everything that has to do with decision making, task planning and the actual plan execution. This division, of course, and Rodney Brooks criticized it from a viewpoint more of AI-oriented stuff, was very little reactive. On the other hand, would allow you to be more deliberative, because you really could decide what to do before doing. You could plan. I remember that at the time, mainly James Albus and actually George Saridis were always saying that there was an intermediate step, which I would say it's what is called now the hybrid and the most usually used architectures, which was a way of having an hierarchy in terms of resolution, in terms of granularity of time and space, but at each level you could have access to the data by all the modules in that level, like a control system. So you really did not have to go to the upper level to react immediately to a very urgent event. Anyway, what happens is that this, at the time and even today, somehow this is what we say that AI is. And what is happening is that this evolved into the type of hybrid architectures I told you about. A lot of, as we saw it here today, and like Michael's architecture, cognitive architectures that came in later, and I have another view of how to organize the systems inspired by the neurosciences. But then one thing that is happening, and you all know, I almost decided to skip this slide. after the other talks, given that everyone talks about similar things, and so you know already, and I would save some time. But there was this shift in paradigm, not recently, but recently became more pervasive, that instead of having this kind of program that looks at input data and outputs data, which is kind of the pre-machine learning type of computation, what you have now is you have input data, output data, and the machine learning computation generates the module that is actual program or algorithm for you. And so when you look at things like the architectures that we were talking about, and I'm going to look into a particular thing, and that's the one I'm going to focus on from now on in my core part of the presentation. What happens is, here we have a common to-task execution pipeline. So I hesitated about what to call this, but I decided to call it a bit abusively model-based, and this one is the end-to-end. So here what happens is the user tells the command to the robot, go to the kitchen and bring me a Coca-Cola or bring me a fork. Of course, you have to use an automatic speech recognition system to determine, to transform into text what was requested by the user. Then you have a module of natural language understanding that provides the intentions and arguments for a planner, that actually uses a knowledge base to plan what the robot should do, and then it has actually to execute it, mapping it into modules that the robot knows how to execute. And somehow, well, this is the old robot we used. You will see it in one of the videos. Now we are using a Tiago. There's also here the loop I mentioned about human confirmation that is also required and very important. But in a sense, this is becoming not saying that it's not good because of that, we are using it a lot, a classical way of looking at it. And somehow, in the sense of those architectures I told you about, this idea of, I mean, you really have the functional modules, you have a sequence of things you have to do, you have different levels at which you react or plan, and then this is the planning level. What is happening is that a lot of this is being done end-to-end using machine learning, and so instead of that you have like a black box that does this into that. We have seen already the pros and cons of that in previous talks. I'm not going to discuss it. I just wanted you to be aware that even though we are looking into this direction, there are people doing it this way, even already in the competitions and in RoboCup and others. Okay, so going quickly through the modules of the pipeline, and I'm not going to go into any detail, and in some of them I would not even be able to. In those which we did not develop, so they are off the shelf. Of course, there was a lot of work involved in making them work well, but for the specificities of what we have. But so the first one, which is the ASR, we are using OpenAI Whisper. And well, this is the claims they do about it, the type of things, for how long it was trained, the ability to be robust to accents, background noise, technical language, and indeed it proved to be quite robust, in particular when you go to an environment like RoboCup and the realistic environments, like if you are in a fair and you are talking to the robot, there's a lot of noise around, and this uses to be quite problematic because you stop there in the pipeline. The robot does not even understand what you're saying, and even if it is quite good in the environment of the lab where you are. But this has really proven to be quite nice. Another one where we already developed some stuff ourselves, and there's a student also working on first steps of his thesis, but already did a lot of work, is on the NLU part, which basically consists on going from, well, we need a keyword detection, like calling the robot, okay, Bob, it's the name of the robot, before we start speaking, then the speech-to-text whisper I described, but then we need to do a parsing of the text in order to filter for us the intention and the facts that we are going to use as actions and state updates, respectively, in preparing the planning part of the pipeline. There are also some things that we use here which are actually interesting. Well, we have an example here. Robot, could you bring the ball from the bedroom to Peyton at the kitchen? And you can identify the intentions. The action is bring, and the arguments of the action, which are facts that we have to put in the knowledge base for the planner, like the object, the source we want to bring, the source location, the person you should bring it to, and the destination location where you should bring it. And there are also small things which are interesting, can also help a lot. The semantic similarity helps us to, sometimes when people don't use the exact words that were expected in the command, you can still map them to the correct actions. And the sentiment is useful for when there's dialogue to understand if the answer was negative or positive. And we also have a text-to-speech system, which is the one that we use for the robots to confirm what it has perceived and also to ask the user to explain better what he or she wants. This is our actual architecture. I'm going through detail of a couple of things there, but I'm not the others, so I don't want you to have to pay a lot of attention to the details here, but I wanted you to at least have a big picture once. Of our part of the pipeline, which is the planning functional architecture. That's why I was also talking about functional architectures before. So basically we have a planning and execution level where we have been using different types of plan representations. I will go through all of them, but we'll focus particularly on this one here. So we have used state machines, PDDL, and now Petri nets. And then of course we have the level, let's say functional level if you want, or execution level, where you have all the systems that actually are able to execute the plans. So we have the manipulation system, which uses a visual serving system, more or less based on the classical visual serving systems, but using some learning to avoid having to put features in the object so that you can really do the grasping using approaches like the ones we saw today and in other instances. So part of it, we do it ourselves, particularly things like determining the objects, how to approach them, how to follow people, detect people, and also another thing which is to fuse information from laser and RGBD cameras to avoid objects which the laser cannot see because they are too small and are on the ground. So this is in the localization navigation part. A lot of perception is what I was talking about, detection of objects and people using machine learning, and tracking also some of the objects that need to be tracked, and the speech part, which I told you already about. So I'm going to mostly focus on this here, and then particularly on the PetriNet part. Okay. So I call this plan representation. So it's not, even though of course there's planning involved, I'm more concerned about how we represent the plans and why that is, and how that is important and relevant. The idea is the following, and that's why I will focus at some point in PetriNets. I will go back to this, but I wanted to give you already this background on this motivation. Over the years, we did a lot of work on making sure that if we have a plan, we can somehow analyze its properties and even be able to synthesize a plan which is optimal with respect to some kind of optimality criterion. And for that, sometimes we need representations which allow us to do that. They may be, let's say, less expressive than, for instance, logic-based representations like PDDL, but on the other hand, they may allow us to do this kind of analysis that might not be possible with the other representations. PetriNets is one such case. It's not just because at some point we dreamed with PetriNets. They kind of do this nice balance. They have, they are represented, they are able to do decent representation, and then they have a huge body of results that we can use for analysis, for synthesis, as we will also see, of the plans, and even to determine a policy instead of, say, a sequence of actions as in traditional planning. Anyway, as I said, we have used over the years different types of representations. We still use, besides the PetriNets, at least this one, state machines that everyone uses for plans. And basically what we are doing currently, and this is very much, again, inspired on things that occur in RoboCup at home, but actually in actual real life robots, there are some things you want to do which you really don't need to plan. I mean, you need, it's like a script of the sequence of things you have to do. For those ones, we use state machines, and I think what everyone more or less uses, each state is a running action plus the state of the environment, and the transition between states are produced by events, triggered by events, and there's usually a goal state where this is, when you check you are there, you are done. And in the raw SMAC implementation, in fact, it's a little bit more powerful than this, or a lot more powerful than state machines, because it even enables concurrent actions. Then, for a while, and one of the videos I'll show you is based on that, we used PDDL. In PDDL, basically what we were using was, we were putting in a knowledge base an initial set of facts about the environment, and the ones that would come from the observation that the robot is doing over time, and also from the requests made by the humans in that pipeline, which had to go there as the goal. And from all this information, and from the information and the models of the actions, we would build a PDDL problem, and we did add cost to it, so that we could determine the plan that was less costly, and where cost is essentially, in our case, a generalization of the cost of navigation. I mean, if you have to take a longer path, it's more costly than if you take a short one. And the same applies to other things like grasping. If you have to do a more complex sequence of motions with your manipulator, this is more costly than a small one, and you choose the plans based on these kind of considerations. Yeah, well, there's a plan validation, and then the scheduler is the one that actually executes the actions one by one, like in the state machine, looking for the state of the environment, checking if events occur to trigger the occurrence of a new action, and so on. That's an example, I mean, of the actual code. You can see here, for instance, the actions move, base, and grasp with parameters, preconditions, effects, which are the ones you would more or less expect. So it's really PDDL more or less standard, let's say. And typically, and I brought this here because then it will be something similar that we do currently with the PetriNets, but this one was already done. Basically, we upload the basic facts, and we go through this loop all the time. We wait for unfinished goals. If they are available, we wait for new knowledge that may appear while the robot executing the things. We generate a planning problem. If it succeeds, we make a plan. We validate it. If it fails, we have to go back there. If it succeeds, we parse the plan, we execute it, and then we wait for the result. If it succeeds, go there again. Otherwise, we replan. Now, going into the PetriNets and starting with an example of how we do it, which actually is going to allow me to tell a lot of the things which are more relevant for the talk. This is an apartment with 3 rooms for which we built a graph. It's more or less, I mean, this graph was for something slightly different, but I used the image. It looks very similar, and for the purposes of what I want to state here, it's good enough. Where we have 3 rooms and 2 types of robots for cleaning, mopping and vacuum robots. We build a graph with the locations where the robots should go. And we actually are able to use kind of an intermediate language that can build a PetriNet out of this, combining all the possible locations, all the possible actions of the robots, that is the vacuuming and the mopping. And so it builds the PetriNet automatically for you, at least for this kind of problems, including a topological map. And I'm not sure, I mean, how many of you, whom of you are familiar with PetriNets, just to see how far I have to go? Huh, yeah, not so many. Of course, I'm not going to give you a crash course of PetriNets in 1 minute, but essentially what's the important things, I hope I won't forget any, are the following. The PetriNets are graphs which have places and transitions, okay? And places represent the state of components of the system, And they can have these black dots there saying that right now this place is occupied, meaning like say, this object is present in this room, that if the place represents that. And the state of the system is actually the distribution of the tokens by all the places. So instead of what happens in a state machine, you can like distribute this over the different places and say, well, Jorn is here, Michael is there, someone who's not here now, like Giulio Sandini, he's not here, and the robot is somewhere in the room. There's an object which is on the top of that table, and so on and so forth. And then what happens is when you have a token, I have a very simple example here on the top. When you have a token or a number of tokens in the input places of a transition, they are connected from places to transitions, you can fire, you enable the transition, you can fire it and move the token. I mean, remove it from the input places and put it in the output places. In this case, it's just one input, one output. And the same for the other place, for the other transition, so this one comes back here. This is the way, this is the flow of the information in the Petri net. And so what happens is, as the tokens change places, the state of the system is changing. And you can associate actions to these transitions, which we call immediate transitions. They don't have time associated. So you just say, well, you are in a situation where you can vacuum, so you order to vacuum. And when you do that, sorry, I have to go back. You go to vacuuming, and now you have another type in the, I mean, in our model, it could be different. But this is typical timed Petri nets. You have a timed transition which tells you how long this action will take. And if actually you make it a stochastic transition, you will represent the uncertainty of the duration or of the success of the actions. In this case, very typically, people use, for reasons I will tell you in a minute, exponentially timed transitions. It's a bit like the Gaussians for many other reasons. The exponentials are quite interesting here because they have no memory, and that will lead us to a particular model that many of you know well. And so these are the models of actions, some more complex than these ones. In this case, the vacuuming, the mopping, and the navigation. So in this case, we had to go, and then we take some time to arrive. So we arrived, and then we say that the robot then is there. So the token would go from here to there to there. So then when you compose all this, the action models with what we got from the topological map, the information about the different locations where the robots might be, and what the robots can do, you get a large Petri net. Sometimes you can really get to a huge one, but if you can do all this automatically, that's actually where things become interesting, because you would not be able to synthesize your plan intuitively. So you have to find ways of doing it and larger plans automatically. And you can, I mean, if you understand a little bit of Petri nets, you can see clearly things going on here, no matter how complex it might seem. So you are in location one. If you go this way, you vacuum. If you go this way, you mop. And meaning that you have options, meaning that you can choose between them. So we are ready for planning, typically. That's what happens. So basically, this is a representation of a plan. So this is what we call a generalized stochastic Petri net, because it includes some stochastic transitions. And the good things with GSPNs is that under certain conditions, which are not very strong, and particularly if they have exponential transitions, and of course if they have action choice, otherwise there's no planning involved, I mean, everything is predetermined. And of course, if we add state action rewards, the state graph resulting of the evolution of the state of the Petri net is equivalent to a Markov decision process, to an MDP. And for MDPs, we know that if we have means of solving them, and we can find a policy. So what is interesting here of this kind of representation is that you can start with a representation which is modular, which you can do for small components that you can compose automatically. You can even put there automatically a lot of constraints which will simplify the state space of your MDP. I mean, instead of like in the traditional rat in a maze problem, letting the rat going anywhere, or even learning to bump into the obstacles and not going there, we say already from the model that it cannot go there. I mean, this is a very simple example. This one is more complex, others are even more complex. But that's the good thing, because the state space will be complex, but the Petri net will naturally constrain it already, and then I will get the final MDP. I can solve it. either knowing the full model, which very often is unrealistic, but we have an open door for using things like reinforcement learning and even using machine learning approaches for larger state spaces, and we have been doing also some of that. So that's the advantage of this kind of representation. So let's go a little bit deeper into what we do here. For the 45? Okay, good. This is say the big picture of what we do. Then there will be one a bit more detailed. We update the GSPN model in several ways, and I think this becomes also one of the interesting parts within the framework of this school from other things we have seen. We have a basic model of things that we know already. I mean, where the objects are, what are the rooms of the apartment, and so on for a domestic service robot. But then we keep creating new parts of the Petri net, either putting tokens or places for objects that we, over time as the robot evolves, know that they have changed places, or creating sub-Petri nets that we add to the structure because, for instance, of unknown objects, I mean, we know how to recognize them, but we did not expect them to be there, and we found them where we were moving around. So, and also it's not here, but it's here also from the information given by the user. So the user may ask things which we did not expect, and we add them to the Petri net. So we can keep growing the Petri net before we actually build a final model. We solve it, we have different ways of solving it, and we finally execute it. And executing means having a policy. We know for each state what is the action we should choose, and naturally this will be always in points where the relevant states for these choices are the ones where we can choose more than one transition, meaning more than one action. The interesting thing also here is that we use a similar representation and reasoning for representing the knowledge and to update it, so which is part of what I was saying. Well, this is back, I think, in 2013, just to illustrate the idea. I will skip this one, but that as we evolve the robot, this is a real image, this is the projection of laser scanners, and we were also watching the objects that it was recognizing. And this is where the robot represents the estimate of what's going on, its location, what it sees, it superimposes the image so that we make sure that it's well localized. But what is relevant, and it's not seen in this part, is that it actually, it keeps classifying the objects that it knows and that it has learned. And currently what we do is we put them actually in the Petri net. We put their location there. We even have something similar to a scene graph where we represent the objects, the surfaces where they are, and the room where the surfaces are. And well, this simulator that we have represents a lot of that stuff as well. Just going to jump in. The detail of that diagram that I promised I would go into next is this one. So this is the part I showed you before, and these are the parts which are more specific now of the Petri net. So the intentions and facts coming from the NLU add facts and intentions to the generalized stochastic Petri net, the GSPN. and also, of course, there's an initial model coming from the known facts, and from that language I told you that generates the world from the fact that it knows the topological map, information about the objects and the robots and so on, and the action models. And all this is used to plus the intentions which specify the goals to build the GSPN that I'm going to use to find the policy. And there are different solutions we use: value iteration, labeled real-time dynamic programming, Monte Carlo tree search. These ones are anytime algorithms. This one is more precise but can take longer. And so once we have the policy, we can actually convert it into the policy of the Petri net executor and execute this part, which is the original GSPN, and send it to our robot and get the feedback and continuing updating the state in the Petri net. We don't update, there are things that we update in the perception that we don't update in the Petri net executor. We just leave it for the next step. So it's like 2 levels of granularity in our architecture. We leave it for the next time we plan, but not while we are actually doing stuff. Yeah, well, I think that's what I just decided some more focus on that part that was relevant. I forgot to skip the slide. So the highlights that and I'm getting close to the results. The highlights are that the default GSPN model has the places for the internal state of the robot, for the environment state around the robot, and also the action models, the ones that I showed you, which include the uncertainty of the success of the duration of the actions, which are important to determine then the policy from the equivalent MDP. And this is something novel we do here. The structure can be changed over time to include new objects and people observed, goal states to add them so that then I can build the MDP. And what is also understood by I mean, if I ask the robot to go to a person which was not yet present in the PetriNet, I'll at least create the structure for that, so that when I see the person, I put a token in the place representing the person. And then of course during execution the state is changed from the actual result of the actions that I observe looking at the environment. Okay, some results. Well, I have 3 videos from different times. I'll go through them not in full detail because I don't have time, but trying to show you some of the things we were able to do with all this this building, let's say. This in Montreal in 2018, this was a quite nice task that we did. It's called Help Me Carry. This one is one of those which is predefined, so no planning involved. This was represented by a state machine, but it actually involves a lot of functionalities. So just in there is asking the robot to follow him. The robot first said, well, I'm ready, so please tell me what you want me to do. And now you see here navigation. This is a robot that we developed in the European project Monarch, and that we used for years also in RoboCup, endowing it with a manipulator. So you can see the robot doing navigation. Inside the room using the map. Outside the map is much more sparse, but he is following the person. At the same time, he is not getting lost because of people crossing the way. So there is a lot of challenges which happen to all the teams. You avoid obstacles and people in general. Over there was supposed to be a car with a bag, so that's the idea of the Help Me Carry. We were not doing manipulation, so we would just ask Justin to put the object ready, and we could pick the bag. And well, just going to the more interesting part, then we pick the bag, we go back, and here there are several challenges. First of all, the robot has more troubles with this part because it was not very well mapped. Then they put this small object that the laser does not see, but the camera over there sees it. You see the head is always looking at the direction of the motion so that it actually sees things like this when it's moving into them using the top camera. It avoided it, and the team was quite excited because we knew this might be a big hurdle and problem. And then it also solves another thing, which is slightly unrelated with what I said, but I think it's interesting to see, which is at some point the robot was slightly lost. It had to enter the room again using the, no, moved too fast, sorry. It was slightly lost. It had to enter the room using this door over here, but it recovered from losing its localization. So it first tried to go to the wall, but then it recovered and it managed to avoid the wall as an obstacle and enter the room. And also you can understand why it brings strangely the bag like that, because it's the only way it can actually enter the room, otherwise it would be too difficult. Would not have space in the door. Okay, so it went on and everything was well. This one is quite recent. It's from RoboCup in Bordeaux last July. And here we need some sounds. Well, we need not so much because you would not understand it anyway, but there's the captions there. So this is something where we were very successful. We actually got an award for the best team doing this there. And even over the years, in the last few years, according to what they told us, there's a task which is called General Purpose Service Robot, and this is actually the reason for a lot of what I showed you today, which you ask the robot a comment from a large set of comments. There's a comment generator, but I mean, there's so many, it's as if there's always something that is unexpected. You cannot just prepare for all of them. You can probably train with that neural net and do an end-to-end approach to this, but we are not doing that at the moment. So basically, then he asks it to go, I think in this case, to look for that guy and then tell something to a guy that is in another room. I don't remember and I didn't see. And so the robot has to do all the pipeline. So interpret the commands, plan what to do. In this case, it really needs to plan. Either looking at objects that it's there, identifying the person, talking to the person, listening to the person, dialoguing if there's a problem, and once it's done, taking the person to another room, in this case. He did not understand initially, I think. Let's skip this part on the benefit of time. So now he asked Simon to follow it, but because it is following, he makes sure that it's Simon there all the time. So it actually, every time you go, it has to do this because you can even be penalized if you don't do it, or even if Simon at some point decides to quit, you should stop and tell and ask for it. So whenever it crosses a door, it does that. And it's actually nice to see. It does it again here. And last slide, promised, well, yeah. But for 1 hour I have 10 minutes, right? I will miss the questions, yeah, exactly. I don't want to miss the questions. This one it would be nice to go in detail, but I won't. I just wanted to tell you that the way we have the setup ready allowed us, I mean, this is a challenge put to all the teams that reach the final 4. And in fact, the final 2. I mean, we were second this year. We're the best European, but there was a Korean team that won here and actually in the domestic, in the standard platform league. They had with the Toyota. But I mean, I think we did quite well. And here, the final, one of the components of the final is you have to demonstrate something that you can do built there in a few days. I mean, not in a few days, in a few hours, because it's like the previous day, you go to the finals and then you have to build it up to impress a jury composed of technical people and non-technical people. So showing that the robot is useful for something, for the task it does. And what we did was, I mean, what the students in the team did, they actually build a story where this guy here had to prepare dinner for a friend arriving. Actually, Rodrigo is over here in the school as well, is part of the team. And the robot would dialogue, would go to the kitchen, search for drinks that he could serve, find out that the list of drinks did not include wine. Then the guy would ask the visitor to bring some wine. The robot would receive the visitor, would take it to the kitchen. All these things were built quickly, just putting up the different modules that we had, and the robot worked flawlessly despite having to be really prepared in just a very short time. This is really my last slide, besides the credits. There are some open challenges and open for a lot of discussion. I mean, these things, of course, there's many more than these, but a couple of them I wanted to bring here. This discussion that I also brought and that we have been having, for instance, in Eurowin and a lot with Michael about the end-to-end approaches versus other type of approaches like the one I showed here, are very interesting because if we want to study the performance of the robot, to benchmark the systems comparing to other systems, right now we know to do it in some ways better than others using the modular approach, because we can go to the different modules, the primitive actions, functionalities, whatever, see, for instance, their reliability, compose it, and expect what is the reliability of the full task. If we go to an end-to-end approach, that's a problem, how we do that, and this is a big deal. At the same time, I said it already, but I wanted to emphasize it, I think that this story of benchmarking the robot system is very important. In robotics, we do a lot of great stuff, we show things. It's a bit what I also did. Look, man, no hands, it works, right? But we don't have, we have some means, but we don't always use them to look at the whole system and check its performance and compare it to others, like what we do in most research and what we do also with the subsystems. Wolf showed that and other people did. Anyway, I just wanted to say that besides Carlos, of course, who is not even here, there were people that were part of the team this year that contributed to what I showed, and people in the past as well. And I just wanted to give them some credit. So, and that's it. Sorry for that.